Hey, my name is Andy Soffer. I work at Google, and today I'm going to be talking about this project that I worked on for about a year and a half. Several other engineers were working on this for many years before I even started. And this one's a particularly fun one for me to talk about because I actually asked this question, how hard could it be, when I started working on this? And so today we're going to be talking about some of the things that make this a difficult problem, and some of the things you might not expect to make this difficult. So let's dive right in. We're talking about integers, and so it's probably worth reviewing some of the details of what integers are in C++. So these are the 10 types that C++ calls the standard integer types. There's signed char, short, int, long, and long, and then the unsigned versions of all of those. And our problem starts right here. Right? These are the types, and the standard actually guarantees very little about what they mean. There's a bunch of properties that the standard talks about, but there's one in particular that's relevant for us today. And that's this idea of bit width. Bit width tells us which integers we can actually represent. Right? There are infinitely many integers, but computers are finite, and so we deal with that by only allowing certain values to be stored. So I've shown here some of the examples of bit widths and what they mean. A bit width of n means that you can represent 2 to the n values, and these are the values that you can represent on standard integer types, right? So if you have an unsigned number with bit width n, you can represent 0, anything from 0 up to 2 to the n, but not including 2 to the n. And then for signed values, you get the same range, but sort of shifted. So you get half negative numbers, half positive. Well, almost half, right? 0 is not positive, but so you get one more negative number in this range. When I was first learning C++, I remember being told that an int is 4 bytes. It's 32 bits. It can hold values from -2 to the 31 up to 2 to the 31 minus 1. And that was probably true on the hardware that I was working on at the time, but it's like not guaranteed at all to be the case. This is what the standard actually says, right? It says signed char is at least 8 bytes, at least 8 bits, but could be more. And an int only needs to be 16 bits wide. It's often 32. 20 would be a perfectly reasonable value for that. So what do we do now, right? I have a number I want to represent. What type should I use for it? Right? The standard doesn't tell me if I have a number that's a million, is an int large enough? Maybe, maybe not. And so the answer is you typically do something like this. You use the preprocessor to ask which platform you're compiling for, and you define an alias that sort of chooses the right type based on the information you have from your platform. Right? So if you're working on Linux and 64-bit x86, long is a fine definition for int64. Right? The platform tells you that that's sufficient. In fact, that it's exactly 64 bits. If you're on different platforms, you do different things. Today, we're actually just going to focus on one platform. The problem's already hard enough there. So we're going to be focusing effectively on x86 architectures, running Linux, compiling with Clang or GCC, and using the built-in standard libraries. And our story starts with a file much like this one. So the year is about 1999. Google's a small company with about 40 employees. And these type defs are added to the code base. As I just mentioned, these aren't correct on all platforms, but we're sort of focusing on the one platform where these are correct. And I think the main takeaway I want you to have from this particular slide is that there's no bug here, right? Like, this problem isn't us fixing a problem that was introduced earlier. Everything here was entirely correct back then. 20 years later, still entirely correct. Int really is 32 bits on this platform, and long really is 64 bits on this platform. Okay, so we're gonna fast forward a little bit, and C++11 introduces these aliases. And this is actually really fantastic. we don't have to maintain our own anymore, right? We can use the standard. It means that our projects can sort of, we can use open source projects more easily if we rely on the standard, because that's what the open source projects are doing. We can open source our own code more easily. They're not depending on things that are internal. And for new hires, right, this is just easier. They don't have to learn new type defs. Like, these ones aren't particularly hard, but you know, little things like this can add up. So this is our goal, right? We want to delete this file, integraltypes.h. And you know, once we do that, we get all of the amazing benefits of the standard library, and hopefully an ice cream party too. But we can't just delete the file, right? Like, everything's going to break if we delete the file. So what do? Well, we have to change every use of int64 to int64_t. And at this point, I should probably mention that Google has about 250 million lines of C++ code. So this is, whether or not this is a hard problem, it's at least a big one. Just changing these aliases isn't enough, right? You also need to manage all of the includes of these things. If you've seen a talk by either Hiram Wright or Titus Winters in the past, you're probably aware that we have a lot of practice with this sort of change. The idea of a global find replace across the entire codebase isn't something we're particularly afraid of. We have a monolithic code repository, and so we can actually do that find replace. But this is where things get a little bit tricky. We're pretty well practiced at find replace when that has no semantic effect on the code we're changing. You know, if we're changing the name of a function or the name of a class, anything that's sort of a drop-in replacement, these are pretty easy. So our first step towards this ice cream party is actually to ensure that these two are actually the same type. If they're the same type, they're drop-in replacements, everything is going to be easy modulo the fact that we have this very massive code base. And in fact, this is the only thing I'm going to be talking about today. All of the other stuff, all of the, you know, the massive find replace across the entire code base, that's a really interesting talk, worth an hour at least on its own, but we're not even going to get there. We're just going to be talking about making sure that these two aliases are the same type. So let's take a look at what these aliases refer to, right? We know that the standard doesn't really guarantee anything particular, but maybe on our particular platform we're going to get lucky and they're already the same. So as I mentioned, you know, there's no guarantees here, but if you're compiling x86, 64-bit, Linux, GCC or Clang using the standard libraries, these are the aliases you probably have on your platform. And you can see the problem here, right? Like, these are all the same aliases. They all reference the same standard integer types, except int64, right? For the one that we have in our internal header, integraltypes.h, that's a long. The standard says it's a long. And so this is what we're trying to do today, right? This is the diff. This one-line change is what we're trying to do. I mean, not even one line, right? This is a 4-character change. How hard could this possibly be? Before we dig into all of the things that actually make this difficult, I want to put you in the mindset that I was in when I asked that question. So I'm going to tell you all the reasons why this is actually very easy, right? Like, for starters, these types are interconvertible. They're implicitly interconvertible. They represent the same range of values, so we're not going to have weird data loss issues or narrowing or anything like that. We already know they're the same type, right? They're not the same type. We already know they're the same size, right? They're both 8 bytes. They have the same alignment, even. And beyond that, they're actually bit for bit identical, right? Like, these things are as identical as they possibly could be, so much so that processors don't distinguish between them. So now that I've tricked you into thinking this is going to be a very easy thing and a talk that's very quick, let's go into the reasons why this is actually quite difficult. But I don't just want to, tell you all of the things that are terrible and horrible and difficult. I want to actually try to learn from these experiences that we've had. So as we look at the examples of problems that we encountered, I want to have sort of like 3 questions in mind, right? And we're going to continue to revisit these questions as we look through the examples. So first, what went well, right? Like where do we see that the choices we made had sort of positive benefits, like positive impacts on the outcome? Secondly, what went poorly? What did we miss in terms of either technical changes or policy we could have enacted, or procedures that we could have followed, where we could have made this easier for ourselves, either in terms of the code at the outset or during the process of making these transformations. Right? These are the things we want to fix the next time we have to do a large refactoring. And lastly, where did we get lucky? I think this is a really difficult one because it's speculative, but it's an attempt to figure out the things that might go poorly the next time if we did something similar. If you've heard of these questions before, they come from the SRE book, right? These are the questions that you typically ask when you're conducting a postmortem. And while we're not exactly doing a postmortem here, I think they're a great way to learn from any experience, good or bad. Before I actually get started with going through these examples, there's one question I want to address that comes up pretty frequently. So if you look at the plan here, right, we're going to ensure that the types are the same, and then we're going to go start changing them. But the question is, why do we start here, right? Why not just start at step 2, start changing the types, and we're going to see all of the problems as we go anyway. And this is a really good question, and it has a pretty subtle answer. Right? Either approach that we take, the end state is going to be the same. We're going to be using int64_t everywhere. It's going to be an alias for long. We're probably going to get our ice cream. But suppose we start changing. Suppose we start at step 2. And this is going to be a long process, right? We've got lots of code we need to change. It might take months or years. And we don't know what we're going to find as we start doing that. Suppose we get about halfway through and we find out this is just an impossible problem. Or maybe it's not impossible, but we just don't have the resources. We can't prioritize it right now. What do we do? Right? We've changed half of these aliases, and we're kind of stuck. Do we change them back? We already know that that took a long time. Do we leave it in this intermediate state? What guidance do we give to developers going forward? Which one should they use when half of their code uses one and half uses the other? Right? This is sort of the nightmare situation that we want to avoid. On the other hand, if we do all of the hard work first to make these 2 types identical, if it turns out that this is really difficult and we have to pause, great. We haven't really done anything that developers see visibly, right? All of the aliases are still int64, and so we can just stop. The short of it is this sort of puts all of the risk and all of the cost up front. And that's really important because it means that you know all of the problems that you're going to see as quickly as possible. So let's start looking at some of these problems. Right? Let's look at what happens here. So we've got this widget class, and it has a member function that takes a long by reference. And the callers pass in int64 and get out a value. Remember that all of the examples I'm going to show you today are compiling just fine when int64 is an alias for long. That's sort of our starting place. So show of hands, who can see how this is going to break? Okay, so you got a couple people. So this is going to stop compiling. And here's the error message that clean gives us. Right? It says, error non-const L value reference to type long cannot bind to a value of unrelated type int64, aka long. Right? Even though long and long are totally interconvertible, pointers and references to them are not. So this is the sort of problem that you see when one of the types is changing, right? int64 is changing between long and long, and the other one is fixed as a long reference. so what's the fix here? Ideally, we would do this, right? Ideally, we would make both of them references to int64. That way, when we change the alias, they'll both change together and the references will bind correctly. This also has the benefit of matching the Google's C++ style guide, which basically says prefer int64 or int32 or any of the aliases that have a size on them, right? We don't know what long means in general on general platforms. We do know what int64 means, and so that's sort of the preferable option. Right, so this is sort of what we would like to do ideally, but it's not always this easy. What if get value is virtual? Right, now we don't just have to worry about changing widgets get value and all of its colors. We also have to worry about widget base and all the colors there, and anything else that extends from widget base and all of the colors there. Right? We had this pretty small self-contained change that we could make, and when it becomes virtual, we now have to worry about the entire class hierarchy and all of the colors there. We've taken this small problem and made it a much larger change that needs to be submitted atomically. So, okay, so what do we learn from sort of thinking about this particular type of problem? I think in terms of what went well, the star here is the style guide. Right? All of the situations I showed you did happen in real code, but they were pretty rare. And that's because we have a strong adherence to our style guide. Right? And that guidance is well thought out. Using int64 over long is actually just a really good practice. On top of that, code owners were pretty receptive to changes. Right? We've really heavily invested on the idea that there aren't sections of the code base that you own and they're yours. Everyone has a sort of joint ownership over our entire code base. And so when I go and say, hey, I need to change this, people are receptive to that. And I got very little pushback on making those changes. But it wasn't just smiley faces, right? There was some difficulty here. And yeah, virtual member functions are a real pain. As you saw in Kristen's lightning talk, we do a lot of automated refactoring. You'll see more of that later on in this talk. But we don't really have tools for virtual functions. This is really just a matter of elbow grease. Okay, but one of the places where we got lucky here was there are actually very few large class hierarchies. Right? There were class hierarchies that we had to worry about, but they weren't particularly large ones, and so doing this by hand was a pretty manageable thing to do. I consider this a place where we got lucky because I don't really see a reason why we didn't have large class hierarchies. We do have them, they just didn't use integers. I suspect that if we did a similar thing and we were working with changing a string type instead of changing an integer type, we would have run into this a bunch. So that's dealing with references. Let's talk about overload resolution. In particular, let's talk about templates. So here we've got a function, clamp above 0, and it just returns the number you passed in, or 0 if you happen to pass in a negative number. So again, same game, right? This is going to work correctly before we make the change to the int64 alias. Then we're going to make the change, and it's going to stop working in some way. Show of hands who thinks they know what's going to go wrong here. Okay, a few more from last time. Good, you're learning the game. So as it turns out, when we change this to be an alias for long, this is going to stop compiling. It's not obvious why this is going to stop compiling by looking at this slide. You actually need to understand something about std_max and how it does type deduction. So let's look at what the standard library says about std_max. This is what an implementation might look like. The body of the function isn't particularly important, but what is important is that both of the parameters here are references to constant t. In fact, they're totally identical, right? They're on equal footing. And so when you do type deduction, there's no way to know which one you should match or if you should prefer one over the other. And so what that means is they both have to be the same. And so if we go back to our example, and we see what happens. Well, int64 starts out as long, 0LL, also long. They match. Great. We're going to instantiate this template as a long. When we change int64 to be a reference to be an alias for long, these no longer match. And type deduction says, yeah, I don't know. It could be either. I'm not sure which one to use. So you're going to get a compiler error here. So this particular problem, either with stdmax or stdmin or a few other templates, this showed up about 1,000 times. That's large, but not particularly bad. Like, at the end of the day, if I had to do that one by hand, I probably would. I wouldn't enjoy it, but we didn't have to, right? Like, we ended up using automated tools on this and sort of finding instantiations of stdmax or stdmin and changing them. So the question, though, is like, what did we change it to, right? So this is one option for a thing you could change it to. And it's a kind of compelling option, but it's not the one we went with. What happens here is you can see the two parameters don't have matching types, right? We've got int64 on one, and we have 0, which is just an int, on the other. But they don't need to match because we've passed in the template parameter explicitly. So now this is just like a normal function call. And so all of the normal implicit conversions apply, right? That 0 will be implicitly converted to an int64 and then passed on to stdmax. And that's actually the problem we wanted to avoid, right? You get all of the implicit conversions that come with normal function calls, not just the useful ones. So I don't expect somebody to pass this in directly, but you can imagine places where you're going to have an implicit conversion to int that now people could use, and we don't actually want them to do that. We wanted to avoid making this common in our code base, right? When you're changing things at scale, you have to worry about what are the patterns you're going to introduce. This is an error-prone one that we wanted to avoid. So instead, we fixed it like this. Right? We brace initialized the 0 and int64 from 0. It's actually the same number of characters as the previous one, which is nice, keeping things as small as possible. And so we wrote a cling tidy check to fix all of these, and we ran it over the code base. So it's worth asking, though, like, why did we have this problem in the first place? Right? Like, we have a style guide. It says, don't use long. But we saw this 0LL all over the code base. Like, how did that happen? And I'm not totally positive about this, but my best guess is that originally people typed stdmax of n, 0, and it didn't compile. Right? And they got an error message, and it said, hey, you've got like an int here and a long, like you should make that 0 be a long as well. And so the compiler message sort of led people entirely telling them the correct thing, that like they have a mismatch of these types. But it led them to create a pattern that we really didn't like. It's like understandable how that happened, but it's pretty unfortunate. So let's change it up a little bit. Right? Let's look at this example with compare. This is effectively the same pattern, right? We've got, again, a template, and it's got these two parameters that are both the same type for the arguments. And we're calling it in much the same way, right? Where one of them has 0LL. But I've left some space, so I'm going to throw in a wrinkle here. And this is the wrinkle. So this is a kind of a weird example, right? Like, why are you comparing bools? I'm not sure, but I'm only showing you things I actually found in our code base. So like, whether or not this is a good idea, it really exists and is a thing that we had to worry about. So show of hands, who knows how this is going to break? Yeah, fewer people this time. So this one is fun and terrifying, right? This compiles, and it runs, and it calls the Boolean overload. So what's happening here? Just as before, we look at the template and we say, well, these two types don't match, so we can't call the template. But substitution failure isn't an error. right? So we're going to silently ignore that one, and we're going to try a different overload. And here we've got this one with bools, and hey, look, long and long both convert to bool implicitly. So we can call the other one. And this is just like subtly wrong, right? 0 is going to convert to false. And if you happen to pass in a negative value, that negative value is non-zero, and so it's going to convert to true. And that negative value should return false, because is greater than 0 for a negative value should be false. But it's going to convert to true, and we're going to see false is less than true, and that's going to be true instead. So this is terrifying, but this actually happened in our code base. Okay. So let's take a look at our questions and see what went well and poorly and such. So for starters, clang tools, like clang tidy is amazing. If you're not using it, you should start using it immediately. Being able to run clang tidy checks over your code base is like a massive win for code health. And being able to write your own and add them to clang tidy allows us to fix these problems that would otherwise be like really difficult to do by hand. Unit tests are kind of a huge win here too, and maybe surprisingly so. As you saw, we had an example that actually compiled, right? It just did something subtly different. And this was caught by a unit test, right? The unit test wasn't specifically for that function, but it happened to be used in unit tests and other things, and this subtle breakage was caught. And the really important thing to note about unit tests here is they're for checking that your code works today. But it's more than that, right? It's for checking that when somebody goes and fiddles with what int64 means, your code continues to work. One of the things that went poorly here is that diagnostics sort of led engineers to write these anti-patterns. And it's really unfortunate. I don't mean to blame like the compiler engineers or the diagnostics themselves. It's not their fault. But in a code base that really highly discourages spelling long, we'd really like to also discourage spelling those literals, and the diagnostics don't match with that. So we solved this, as I said, with a clang tidy, but what I'd really love here is having compiler diagnostics that are scriptable, right? So that the message that they give can be more meaningful to developers. Overload resolution is just really complicated. Right? Like staring at this for more than a year, not this particular problem, but like all of the problems that showed up. I can tell you some best practices of things to do and not to do when you're designing your overload sets, but it's just really complicated, and I don't think it's reasonable to ask engineers to have all of those rules memorized. And I actually don't have anything here for where we got lucky. If you see something, I'd love to hear it from you, because it seems like there's just good or bad, and I probably have some oversight here. But okay, so we've spent a while talking about integers and things related to integers, and let's continue to do that. Let's talk about format strings, very integer related. So we've got this function, string printf. You probably have something similar in your code base. This is effectively just printf, but it writes it to a standard string rather than to standard out. And everything I'm going to show here applies equally well to printf and all of those sorts of functions. This is just sort of easier as an example to show. So we've got this function. It's just calling string printf. And yeah, this is the entire example. What's going to break here? Show of hands. Anyone see it? Okay, looks like about half. So this is going to fail to compile. And the reason is that we have format string checking turned on for printf, for string printf. And we've said with that %LLD that we expect this to be a long. When we change int64, it's no longer a long, it's just a long. And so we kind of have to change %LLD simultaneously. That's a difficult thing to do because there are something like, I don't know, a few 100,000 uses of this function across our code base, right? We're not going to change those all simultaneously as we change our type. So we've got to come up with some other solution to change these. Now, the standard provides some macros that kind of paper over %LLD, so it'll work with whatever int64 means on your platform. Those are kind of ugly, and so we didn't end up going with that solution. But this also isn't even the full scope of the problem, right? Like a few 100,000, but there's more. Because other people added this attribute to their functions, right? It says like, hey, I want format string checking on this function as well. We had a few hundred of these, and a bunch of them were actually marked virtual, right? So now you have hierarchies of these things that all need to be changed simultaneously. So what did we do here? This is the change that we decided to go with. So we replaced string printf with this new thing, absol stir format. And again, we're going to roll this out using a clang tidy. So we're not going to be changing these manually. But this does all of the same format string checking, but it's a little looser with the types, right? So it's a template, and so it's going to infer the types from the arguments you pass in. And this is going to work with %d and still print the correct type, right? There's not like a bug here by getting rid of that LL. It sees that you have a long or a long, and it's like, great, I know how to print an integer. So this is actually really wonderful. Stir format is an amazing thing, but it's amazing for reasons that don't even have to do with the integers here. Right? So for example, with string printf or any printf-like function, you can't pass in a std string directly, right? You need to call .cstir if that's what you want to do. But stir format, totally fine, right? It takes a string view, and everything just works. It prints it correctly. So even though we didn't technically need to make this change for the purpose of changing int64 to int64t, we decided to do it because, well, it's nicer code, and like honestly, how hard could this be? So yeah, as shown, if you try to make this change, you're going to get a linker error. This is probably the most baffling error message I've seen. Right? Like undefined symbol, puppy, cuteness. I'm staring at it. It's right there on line 10. Like it's defined right there. So what's going on here is kind of fascinating. It's actually not visible on this slide. You have to dig into the differences between string printf and stir format. So stir format takes, as you'd expect, a format string that's a const char star, and then ... right? It takes C-style variadic arguments. One thing to note about C-style variadic arguments is that they're all passed by value. On the other hand, stir format, so it's got this format spec thing that basically you can think of that as a const char star as well, but it takes all of the arguments for the format to be formatted by const reference. And that's particularly important because, well, we're allowed to pass in strings, right? We don't want to be copying that string every time. And that difference is actually exactly where the problem lies for us. Now, I'm not going to show you the actual wording from the C++ standard, because I know we all have it memorized. But the relevant section here is this basic def ODR paragraph 5. Roughly speaking, what it says is if you're going to pass a variable by reference, it must have a definition. Initializing a static class member doesn't count as a definition. We have people on the standard here that can maybe explain why. I have no idea why this doesn't count. But if you make the variable constexpr instead of just const, that does count as an inline definition, at least as of C++ 17. I'm certainly hazy on the details here, despite having dealt with hundreds and hundreds of these. But this actually gives us the solution, right? So here's the problem that we had again, and the solution was this, right? Change static const int to static constexpr int. Now suddenly we have a definition, and everything works. And so again, this is a thing that came up hundreds of times as we're doing this, and we're not going to do those by hand. We built a Clang tidy check to make these changes across our code base. And that's, I believe, like turned on. So future uses of this, like if you accidentally write static const int in the future, you'll get a warning that says, hey, you probably want this to be constexpr. So once again, like Clang tools, amazing here, right? Like super helpful in actually making these changes that otherwise would have taken years of many people's lives and carpal tunnel syndrome to actually implement. Like we can have robots do that work. This just like would not have been possible without them. On the other hand, like there's a lot of bad things that happened here, right? C++ is a really confusing language. And I don't intend this to be like a dig at anyone on the standards committee. It's a really, like, some of these rules have really good, fundamental, important reasons, but they are confusing. And even the ones that don't have really good reasons, like, there's just too few people working on too hard of a problem. Like, either way, this isn't any person's fault. But regardless, it is complexity, and it does harm the developers who are using it. Another problem is that this missing definition was found particularly late in the process. Right? What I mean by that is that probably when you have a variable, you want a definition for it. Like maybe some cases where you don't need it, but for the most part, this is a thing you want. And we didn't find it until you actually went to use it. Right? We found it when we made a totally unrelated change. It would be really nice if we could find these things earlier. And of course, I can't give a talk without mentioning Hiram's law, right? Nobody promised that string printf wasn't going to ODR use its arguments, but with a few 100,000 calls to a function, someone's going to end up relying on that fact. And in this case, hundreds of times this was relied upon. One place where we got actually really lucky here is that these format strings were checked at compile time. Like almost every format string we had was checked at compile time. If we didn't have that, right, there's no way we know that the changes we're making are safe, right? We would change it and it would still compile, and honestly, probably still work, right? Like, but when you pass something, when you pass a long and the format string says long, that's undefined behavior. Like in practice, it's probably fine, but if I'm making 100,000 changes like this, that's not a bet I'm willing to make. And so having this format string checking was really vital. So we got one more section here. Let's talk about performance, right? So again, this is the change we're making. And remember when I said that processors don't distinguish between these two types? Yeah, so you're going to be as surprised as I was when I tell you that this actually caused a 2% regression for web search. This like totally blew my mind when I first learned about it. Kind of ridiculous. But the key here is profile-guided optimization. Right? That's what's going on that ended up causing this regression. The idea with profile-guided optimization is that you take profiling samples from your running binary, and you're going to use them to optimize the next version of your binary. Right? So for every function that you're in your binary that you're running, you're going to jot down some performance notes, and when you go to recompile, you're going to use those to improve branch prediction, cache locality, or any number of other things. But here's what the compiler actually sees, right? int64 is an alias. The compiler actually sees the underlying type. And so in the old version, when int64 meant long, the compiler sees the first thing here, my function of long. In the new version, right, we have a totally different function, my function of long. The compiler doesn't understand that these are probably the same function, right? They have the same name, but they have different signatures. They could be wildly different. And so as far as it can tell, this is going to be completely different, and it throws out all of the profiling information that it gathered from the previous round for this function. Right? The optimizer is sort of treating these as entirely different functions that might need to be optimized differently. So a couple things went well here. First, Clang has this flag, fprofile remapping file. And this says, this is a file where you can tell Clang, hey, I know these functions are different. I know they have different signatures, but like, don't worry about it. I promise they're the same. You can reuse the profiling information for them. And that's what we did. We said, anywhere you see long or long, don't worry about it. They're the same. So this made this a relatively easy fix. I believe most compilers that allow you to do profile-guided optimization have a flag like this one. Another thing that was like really crucial here is that we could test this, right? That we have performance tests that we can run, not just micro benchmarks, but across the entire binary, right? We can do this before we release the binary. Like that's critical. If we had to wait until we release the binary, a 2% regression, 2 might not sound like a particularly large number, but think of that as 2% less queries per second, or a 2% larger electricity bill, or you need 2% more computers, right? Like any of these options is a lot when you're serving something like Google search. One place where we actually had a bit of a problem was that like we weren't able to explore this early, right? We knew when we started this problem that we're going to want to change int64, and maybe that has some performance implications, but we couldn't test it early, right? You can't actually test this until you measure it, and you can't measure it until all of the code compiles. So this was like the last thing that we did. What I'd really love here is being able to take a profile or profiling data and sort of selectively throw out pieces, so that even if we haven't made this change, we could throw out the pieces related to long or long and see how that would have affected compilation. And that way we would have been able to get a proxy, or like an approximation for this information much earlier. And we would have known if there were issues that we need to consider. We got lucky here, actually, in a kind of terrifying way. One of my coworkers just mentioned, like, hey, you probably want to check this. I had no idea that I needed to check this, right? And I would have gone on just, yep, let's make the change, we're ready to go. And that could have been pretty disastrous. So yeah, this is definitely something that in the future we need to make sure we write down and make sure that engineers know is going to be a problem for this sort of change. Another way in which we got lucky is like, hey, what if this didn't work, right? Like, this could have just not worked. There could have been other like functions that had long and long that really needed to have different profiles. And when we told the compiler, like, hey, don't worry about it, they ended up using the same one. This could have caused regressions too. That could happen, and it's not a thing that we really had an answer for. So, sort of summing up, looking back at the good and the bad that we identified through these things, I think there are 3 major themes here. The first, so Hiram Wright of Hiram's Law fame often says that you're eventually going to want to change literally every line of code that you write in your code base. And so you should plan for that. Like, this is, I think, really well exemplified here, right? Like, what could be more stable than a primitive type alias? And if you're thinking like, yeah, but like we're not going to change int64 in our company, you're probably right. But I think that this is just one example of that sort of situation. And this sort of thing is going to happen eventually for some type. Problem might not be as big, but it's going to happen somehow. So secondly, like C++ is just really complicated, right? There's this subset that we talk about that we call modern C++, and it's certainly simpler, but for the most part, our code is not just in modern C++, right? It's a mixture of legacy and modern. And insofar as we have legacy code, we need to understand all of that complexity. It's sort of unavoidable. As our code bases grow, we need a way to manage that complexity. There are a lot of tools at our disposal here, all right? Like style guides, refactoring tools, improvements in compiler diagnostics. Those are just a few of the things that we found valuable for managing that complexity. And lastly, like quick feedback is absolutely vital here. If you look broadly at the problems that we discussed, the easiest ones are the ones to adjust where we like actually had a compiler error, right? We found out immediately that this was going to be a problem. As we pushed back feedback further and further away to linker errors, to test failures, and ultimately like performance regressions, the costs became much larger, and the risks associated with that also became larger. This is why I think things like clang tools and clang tidy sanitizers are so incredibly valuable, right? Because they take problems that you wouldn't find about until much later and make them apparent very quickly. And with that, I want to say thank you and open it up for questions.